I'm honored to welcome Sir Konstantin Novoselov, Nobel laureate and professor at National University of Singapore. He recently joined our advisory board to bring in his expertise in advanced material science. His work includes research on graphene, which he earned him his Nobel Prize in 2010. We have his keynote today about materials for the future. Please, Doctor.
Thank you. Afternoon, everyone. It's really great pleasure to be here. A quick statement that I'm a simple physicist, so I'm sort of falling in between the cracks here. But what gives me some hope that in the second talk today, we were told that material science is one of the focuses for Abu Dhabi. So hopefully it will work in the future. But also, my hope is that placing material science talk in this session places me in one of those badly connected points on the previous talk. So hopefully something will get out of it. So, but let me try to make myself relevant, and one of the easiest ways through the sustainability story. So of course, these days we really talk a lot about how to make ourselves sustainable. Current distribution, you know that even though there are quite large efforts towards this, but in reality we're still not very sustainable at all. And the problem is that in reality the diagram shouldn't be look like this. It's actually so. Of course, we really want to be fully renewable in the future. The problem is that the real relations between different sources of energy is way more complex, because you really have to think not only where do we get our energy, but also all the complexity of the network in terms of the conversion, the transportation, the storage, the utilization. And if you will ever want to switch completely to the renewables, this diagram is going to be even more complex in the future. So how do we how can we work with this, and how can we create a new sustainable system? Well, first of all, we really have to figure out what kind of model should we adapt, because these days there are lots of different models. Some of those have been tested in different countries and already failed. But so you can think about building yourself in terms of the electric and hydrogen economy, or maybe just hydrogen slash carbon economy. Maybe you don't need to think about those at all. You just plant a lot of forest and in response of the consumption of the fossil fuels. That's it. So, but the problem is that each of those scenarios, whichever you take, would require a lot of changes in the policies and a lot of investments, and that's the limiting factor at the moment. So the policy and the investment. So generally, where the investments are coming from. So you basically optimize your energy production network for profit. And now what we're really trying to do, what we need to do, is to optimize it for sustainability. So and that's the question is, can we optimize it in such a way that the sustainable solutions are profitable at the same time? Generally, so currently we have strongly centralized energy supply systems, which is not that bad in terms of it's being robust. It gives you a predictable output in terms of energy supply. It's easy to regulate. The problem is that it's purely supply driven, not very flexible, and so it's not very customer oriented. An alternative is, of course, the decentralized. That's exactly what we heard this morning. And if you have a decentralized system, what you need is first of all new ways of producing energy, and it should be local, and it has to be linked to the local economy, and that's what we see a lot with the hydrogen economy, for example. But also you have to put quite a few smart contracts. So that's exactly what you have to invest in: advanced systems of energy production and smart contracts there. So let me talk a little bit, focus on the materials today. And of course, we all know that materials are quite important in human history. So we will name the ages we live in by the names of the dominant materials. There was a Stone Age, the Bronze Age, and the Iron Age. And a good question would be to ask which age do we live in right now, because and probably for the first time in history we have quite a choice. You can call it the Silicon Age, or maybe the Digital Age, or the Nuclear Age. But what I would like to argue that probably we need to use this opportunity and not making this blind choice and really leave it a little bit open. Let me show you what happens when we bet everything on one material, and we take silicon technology as an example. So this is the periodic table of elements which we used in our silicon technology prior to 1990. Really only a few elements there. So there is, of course, silicon, there is boron and phosphorus for doping, aluminium is the interconnects, and then hydrogen, oxygen is for passivation. So really simple technology, even I could possibly do it. And then after 1990, our transistors started to get smaller. We needed thinner interconnected lines, so we started to use copper instead of aluminum. If you use copper, you need some work function matching materials. You need some diffusion barriers. So we added a few elements there, but still manageable technology. So these days, what we have is extremely complex silicon technology, and it's basically because we know silicon so well and we already invested so much money into it that it would be extremely costly to switch to a new material. So we keep adapting the old, 50 years old or 70 years old technology to the new needs, but that increases the complexity dramatically, and it's really instructive to compare the number of elements which we use in our silicon technology with the number of elements which you have in your own body. So actually, looks like our silicon technology is by far more complex than what is happening in your body, which is of course not true. We are by far more versatile. So and that's actually true not only for electronics, it's also true for construction industry. So we rely on the strength of steel. So only few materials basically determine our world, and we bet on those. But that's not the optimum outcome. That's not the optimum technology. Ideally, you don't want to be the slaves of those materials. You want to be able to, so rather than designing new devices within the constraints of the old materials, you want to be free in designing new structures and then find the right material which would work best for your applications. And we have those technologies. We call them composite materials or heterostructures, and we see some good examples appearing these days, but it's still, so those technologies are still few and far between. So ideally what you would really like to have the ability of designing new material from scratch on the for a particular technology. So if someone needs to design a new semiconductor device, he or she would take would design a new material for the specific purposes with the given band gap, with the given work function, and then be able to create a composite material which does exactly what you need for this or another device. So just maybe a few words. So I promise I will come to the future materials just in a second, but I will just give you a little bit of a story about graphene, so which is a two-dimensional material, one atom layer thick. We're still playing with it, and so these days there are ways how to produce it in large quantities. One of the best ways to produce electronic grade graphene with the chemical vapor deposition, when you run carbon-containing gas on top of the catalytic surface, and then this gas cracks into hydrogen and carbon, and hydrogen you can use, it flies away, and then carbon rearranges itself into graphene. And of course it's quite expensive process, but then at the same time it can be made quite a cheap one, even negative cost, because we waste so much of carbon-containing gases, like we usually burn methane, the supporting gas at the oil fields or at the petrochemical plants, and in those flares we have everything what we need to produce these functional carbons, either graphene or carbon nanotubes, for example. So you can use the heat, you can use the gas and turn it into hydrogen and carbon, and we work with them. So we have those machines already. The problem, and actually, so those are thermal machines. The plasma machines work even better. You don't need to rely on the flares. You can do it pretty much any way you want. And of course, the problem was that these days, so this way we produce quite a large number of graphene and functional carbon, and so if it is combined with the hydrogen technology, you would be producing trillions of tons of carbon. No one needs this amount. So just for you to realize how thin is graphene, so one of the applications is the use as the touch panel in your mobile phones. But if you replace all the touch panels in the world with the graphene touch panels, you will only use 1 kilogram of graphene a year. It's just how thin it is and how light is carbon. But luckily, construction industry can utilize large quantities of this material because by adding a minute amount of graphene into concrete, you increase the compressive strength by up to 50%. So which means that you would use less concrete for the same strength of the building, and concrete industry is one of the largest CO2 emitter by itself. So you basically take carbon from the atmosphere, add it into concrete, and you reduce the CO2 emission even further. And what people are playing with now is the conductive concrete, green concrete. So by adding, so we do it with graphene, other people do it with other materials. You can turn your concrete slab into a battery, and so you can store energy in those. And so there are other ways how to produce graphene, but the big breakthrough was when people realized that graphene is not alone. There are other materials similar to graphene, only one atom thick, but they would have different properties. And that opened up to the new direction of the synthetic materials. So basically, if you have access to those one atom thick fabric of different crystals, you can create three-dimensional stacks of artificial materials, and you can basically design your materials from scratch. And that's exactly what I was talking about before, that these days we can engineer new materials with the atomic precision, and we can design them to either work as an electronic devices, tunneling transistors, or as the photovoltaic devices, LEDs, and so on and so on and so on. And now, so this looks like the dream of any material scientist. So we have the technology, the platform to design pretty much any material you want with the atomic precision. It's not entirely true, but it definitely created very interesting horizons in terms of material science, and that's what basically made us to think what's next. So if you already achieved the ability to create tailored materials with the predetermined properties with the atomic precision, what would be the next step in your in the materials design? And rather than just giving you the answer myself, let me show you how other people before me answer this question. So this is, I'm sure that lots of people recognize this movie. It's the movie from my childhood. It's Terminator 2. For younger people in the audience, it's actually worthwhile watching it. But so for younger people in the audience, so the movie was made in '91, and the plot of the movie is that a robot from 29 sent back to 1991 to kill Sarah Connor and her son. And the only reason I'm showing it to you is to show how people back in '91 thought our future materials should be. So they didn't think about two-dimensional stacks. So they wanted these alive materials which can change shape, which can change color, which can be adaptive, which can have these self-healing properties, and so on. So now we are, okay, so it's 25, but we still have some time to go. The problem is that unless we do something radically different, we don't have any chance to fulfill the dreams of that Terminator 2 movie. And the reason is that our technology is fundamentally top-down, because what we have, that individual components in our technologies, they're usually not functional at all. So the functionality, the complexity comes only on the system level. You take one cogwheel out, neither the cogwheel nor the system is functional anymore. And this is true about the robotics. It's true about the clockwork making. It's true about electronics. Now, what we would like to do is to learn a little bit from the biological systems, where the functionality is spread across all possible levels. So individual proteins, they're functional. The membranes of the cells, they're functional. You can take a membrane from the cell and you can use it for water desalination, for example, or you can use it for DNA translocation. So there are so those individual components, they're functional in their own rights, and that's what we would like to do with the future materials, which would be able to be active in their own rights. So let me just give you an example of what I mean. One of the application of graphene is in water desalination membranes. So it works well, and the membrane technology is becoming more and more important. Here in Abu Dhabi, it's very important. In Singapore, we use, so 99% of our water goes through membranes, usually polymer membrane rather than graphene membrane. So they use graphene membranes for other purposes, but it doesn't really matter which membrane do you use. You would still have to put a sensor downstream to control the quality of water, which sends a signal to the computer, which analyzes the signal and sends a signal to the actuator to open or close the valve. But now think about creating a smart membrane which has internal structure which is sensitive to the presence of certain toxic species, which can change their conformation and can react on it and can do something upon the presence of those toxic species. And it means that your material itself, the membrane, acts as a sensor, as a computer, and as an actuator at the same time. So, and this is actually, so that's this digital world is one of the is becoming a reality. Now, what we realize that it's not very simple to create those smart materials because they essentially need to be out of equilibrium, and we try to achieve it by combining many different materials. So we work with a huge variety of organic and inorganic systems, and we create them in a so-called degenerate metastable state, which is very, very similar to the state of protein molecules in your body, because so those protein molecules, they can exist in different conformations, each carrying certain functionality. And those conformations, they're spaced not that far away in terms of the energy, so it's easy to switch from one to another upon the presence of the certain stimuli, and then you can, with the external factors, you can switch them and make them functional and create certain functions for them. So that's what we're trying to do with our materials, to make them active components in our technology. And that's where AI comes from, because comes in, because the traditional physics approach which we have, they're not very helpful here, because physicists don't like dynamic systems which change in time. So we utilize more and more the so-called dynamic machine learning, and of course you need to feed a lot of data into those, and so that's what we do with the help of the robotic labs. So when I talk about robotic labs, usually people think about something like this. So so we have those as well. So you just film your student and then just replicate the same in the form of a lab. Honestly, it's a little bit. It's not ideal. It's a bit clumsy. It doesn't understand when you shout at it. So that's. We use them, but not as much as we would like to. Most of our labs are quite dedicated, and so they designed to do very simple materials, but in large quantities, so to feed our AI systems. And so these days we are trying to combine the two approaches, make it modular and make it more adaptive through the modular systems. So what I wanted to tell you is some advances in terms of the AI, and so with the advent of AI models, LLMs, Chat GPT, we thought that's really a good time to apply AI for the design of our materials. In fact, we started quite a bit before that, and we jumped into very complex problems of high entropy alloys. I won't go into details, just to say that one of the applications in material is in catalysis, and these days it's really a big problem how to replace platinum for electrolyzers. So electrolyzers and fuel cells is very important technology, but to produce hydrogen, you need to split water, you need platinum, and it's becoming expensive. So so a lot of efforts are devoted towards search of new catalysts which don't use platinum. So we have some progress. I won't go into details. Some very interesting, very promising materials. They usually very complex alloys, and we realize that we cannot understand their behavior unless we do quite a lot of AI, and we created big databases of different alloys, of different defects in different crystals. We got an open platform, anyone can play with it, and we had to put some quantum data, quantum descriptors inside, so it's partly physics-informed model. The problem is we failed miserably. We couldn't describe with all these efforts, we couldn't describe what we observed in the experiments. Again, the experiments are very promising. The AI didn't help at all. And to be honest, we are not the only one here. So there is another very influential paper, which again 2 years ago, when ChatGPT demonstrated such a fantastic success, everyone jumped into the AI-assisted design of materials. There were some success stories, but not as much as you would like to. So here is the attempt from Google. They, with much larger capabilities, they screened more than 2 million different compounds. They identified almost 400,000 those which are stable. Attempted to synthesize 58, synthesized 43, but none of them actually turned out to be new. This is really, it shows that we really need to go back into the drawing board and think about new ways how we should attack this problem of the material design with the use of AI. And there are two basic problems here. One is that usually in the databases which we have some very simple, pure materials with only a few elements in the unit cell. The problem is in practice we don't care about those materials. We don't use pure iron, so we use steel, which is the alloy of iron with carbon, with nickel, maybe with chromium, with vanadium, and even that is not enough. So we also try to modify the morphology of those crystals, and we even go further. We try to create them in terms of nanostructures, for example, for catalysis. Same with silicon. We don't use pure silicon. We use doped silicon, create p-n junctions out of this, create complex nanostructures. And again, all this information is not being picked up by the training in our AIs. The second problem is that usually we have these relations between the structure of the materials and the properties, which is great for the textbook, The problem is this story misses completely the question of the synthesizability. Even though you can predict it, can you actually synthesize it? So can you kinetically get into this particular state? No one really knows. So that's why we are trying to an alternative way how to do it. We don't completely ignore the material structure, but we start with the material synthesis and we try to link it to the material properties more or less as a black box with some material structure as an input. And for that, what we do, we create a very complex landscape by observing in reality how the synthesis goes through. We create a very complex reaction landscape, because when you mix things together, you would hope that everything goes according to the equation which is in your textbook. In reality, it's not. It goes just through multiple pathways, multiple channels, and then only the dominant, hopefully, is the one which you need, but sometimes even not. And then we have to combine all this information together, experimental, computed, and then just build the AI model, and then test and verification, and just close all this loop. So just to show you the examples of the dynamic of the applications of machine learning for the dynamic systems. Last year, Nobel Prize was given for the creation of AlphaFold, which is the identification of the lowest energy state of the proteins, the folded state. So here we try to ask ourselves about the dynamic behavior, and the dynamic behavior plays important role for many other new materials which we are trying to synthesize. And then we have to build machine learning which work with the with time sequence data, and we have to it's physics informed AI. I won't go into details. We try to adapt the same for the analysis of the stock market. It's basically the same time domain data. The problem is that it's physics informed, so there is one driving force. It's the Ansaga principle. We're trying to find the same for the financial market as well, which is not that easy. But at least in terms of physics, it works well. So we can predict the behavior of those folded, of the folded and the unfolded, of folding and unfolding of those proteins, and it really gives us hope that we can go to synthesize new materials with this novel dynamic property. So here is an example of a high entropy alloy which has this self-healing property. It's not Terminator 2 yet, but it's going towards there. So what you see there, the little dots is the TM image. The little dots are the individual atoms, and then we drill a hole through it. And then if you design things correctly, it should completely regrow this hole and completely close it. The range of parameters here is huge. If we try to predict it from the first principle calculation, you would fail entirely. So we now apply this dynamic machine learning, which we design to the question of the atom dynamics in such complex alloys. Another example is the smart nanocapsule for drug delivery, which need to open or close depending on so they need to go through your stomach in the closed state and then open up only in the intestine or in your bloodstream. I won't be able to show you microscopy pictures, only the cartoon, but basically we can create macroscopic systems which operate on similar principles and can do some crazy mechanical motions depending on the external stimuli. You shine light, or you change temperature, or you change pH, or you change humidity there, and then even more complex is the biotic abiotic interfaces. So we play with those bacteria which can generate electricity, and which can generate electron during their life cycle. And then if you can connect electrodes, you can extract some current from it. It's basically biological fuel cells. You don't need to build gigafactories for your batteries. You can just start with a few bacteria, give them sugar, and then they just grow into a fuel cells by themselves. So we're not the only one. There are lots of people who work on this. It's a good fun, but again, it's complex dynamic system which and we hope to use dynamic AI for this. Now, in the last 3 minutes, let me talk a little bit of a different topic. So I was talking about AI for material design. Let me now talk how materials can help AI in the future, and the motivation here is the sustainable computing, because you know that for many years the sustainability mode for our computations was supported by 2 laws, the Moore's law and the Denon's law. Moore's law guarantees that you double the number of transistors every 1.5 years, and the Denon's law tells you that even though the number of transistors goes up, they're actually getting smaller, so the amount of energy which you consume per area doesn't increase. So which was a happy growth of the electronic industry, until recently we started to face this power wall, because our transistors getting smaller, the leakage current goes higher, they start to overheat, and so on. So there are, of course, ways how to, and actually the problem is going to be even more severe, because we got, with the advent of the artificial intelligence, I don't think quantum computing is going to be here in the next 5-10 years yet, but the AI is pushing really hard, so it will increase the energy consumption dramatically. It's 5% now. Within the next 5 years, it will probably go towards 7, maybe even 10% of the total energy consumption. So what you try to do, so you try to design alternative computing methods. There is neuromorphic computing, there is quantum computing there, and recently people started to work on the probabilistic computing, and I would say this is probably the most realistic way how to reduce the energy consumption. So what it is, so in the classical computers, we use zeros and one to represent information. In the quantum computing, you use the whole block sphere, and you use the entangled states between 0 and 1. And in probabilistic computing, you use the probability to describe your system. You create weighted random number, which describes the connections between different elements. It basically there are several ways how to do it. Magnetic tunnel junctions is probably the most popular. In my lab, we have a system which operates on the superconducting system and on the superconducting nanowires. And for most of the problems, what you do Boltzmann annealing to find the solution, and it works fantastically well. So we apply it for image generation and image recognition, and so you can do portfolio optimization. We are not as lucky as the previous speakers, no one pays us for that, so we are theoretically rich, but not well, experimentally rich as well, but not with the real money. Solving complex logistic systems, it's problems is another application. So and potentially the same probabilistic systems would be good for AI applications, though it would require a lot of investment in terms of the algorithms as well, not only in terms of the hardware. So I think I will stop here, just summarizing that. Hopefully we'll start working with the smart materials which can adapt to the external environment, and those are the kind of materials which we typically need for AI applications. And so it's a good time to work with those materials now. Thank you.
Thank you, Professor. We can take one question.
You just shout, guys.
Thank you, Professor, for the fantastic talk. My name is Sofia Al-Hashmi from NYU Abu Dhabi. I have 3 questions. So for the first one, you spoke about the self-healing graphene composite material. The self-healing process, from my understanding, is not thermodynamically favorable. You need to apply an external heat or force for it?
Right. So yeah. For the healing, no. It's entropy driven. So that wasn't graphene. It was high entropy alloy, and it's the entropy driven process. So we're really trying to learn from the biological systems where the entropy drives many processes. So that one is the entropy driven. So it's
perfect. Thank you. And for the synthesizability prediction for the materials, you said you were able to get the ML to be able to trap the synthesizability if you had the inline analysis along with the basically the properties being measured inline. So this is a self-driving lab, from my understanding, right?
Right. Yeah. So basically, we create the energy landscape for all the possible chemical reactions. And then experimentally, we know some of the intermediates. We know that those correspond to the saddle points, and then you just reconstruct the whole landscape of the chemical reactions from those saddle points. Plus a few computations, and then you just, if you know the connections, so how these intermediates are connected, you know that it goes through the local minima. So it's quite an exciting mathematics. I'm not. I mean, I can talk about this, but only so much. So it's quite a complex mathematics there. So we can probably try to write a few equations later, but I probably would refer to our recent paper. Right?
Sure. All right. Thank you. Yes, and one more thing. So yeah, for the inline analysis, this is real data point, right? And then you feed it back to the ML model, or this is not necessary for you to be able to capture the energy landscape?
So the energy landscapes. So there are several. So the data merging is a very important point there. It's actually much more complex than in the usual AI, because there we merge the information about the intermediates, which we measure directly through spectroscopy, through mass spec, and then so you have the theoretically computable chemical reactions, and then you do some molecular dynamics as well. So and then you have to combine those 3 in some model which is mutually coherent, So that's a big problem by itself, and then feed it into the machine learning model.